Hey, what's going on YouTube? It's time for another Advent of Code. This time we'll be tackling day 9 of 2024. Yes, I know I have not yet posted a day 8 video, and that is because I have not yet attempted it, nor have I really looked at it. We're going to do that at another time. Saturday nights are church night for me, so I have my priorities elsewhere. But tonight, we'll do part 9, and maybe if we get done early, we'll do part 8. Or I'll save that for tomorrow. We'll see. I'm excited. So some pretty cool stuff here. I've been playing around today with visualizing some of these, and I noticed on day 6 was a grid problem. And so I'm looking at using Find to visualize that grid. And so the idea here, the only thing I don't like is the font is pretty small. But as you can see here, I've got the entire grid loaded on the screen. And the idea is that we would highlight the path as we process and build a framework so that this is generalized so that any grid we could load and we could visualize some sort of walking path with the data. It doesn't look great here. So that's just from day 6, something I've been working on. But we'll tackle that when we get there. I think it would be pretty cool to highlight these cells a different color as we traverse the grid and produce some sort of output. So I'm building that into my matrix library just to allow us to quickly kind of spool up this visual and get an idea of what it might look like instead of just printing it out to the screen. It's going to take some time to work on it, so it's not quite finished yet, but I think we can do some pretty cool stuff with grids later on, and just kind of gives me some ideas for how we might visualize some of these things. So taking it from just being raw text and some problems to maybe some tangible visuals that might look cool or perform, pretty neatly in certain ways. So this is from day 6. So we're looking a little bit back here, but the framework I'm building could be applied to anything else. So as we get into day 9, we'll kind of dig in there and see really where we're headed with day 9 as soon as that releases. Again, I missed day 8 last night and haven't really even looked at it, so I'll tackle that at a different time. We'll go and do day 9 tonight. If you guys have any questions, let me know, comments. But this is kind of start of a framework for visualizing what some of these problems might look like. So the idea is that each of these cells, text blocks, we would highlight the background as we traverse the grid, and we would build some sort of visual aesthetics with that so that we can see, like, as we're tackling a grid or we're traversing a grid, we can see us solve those problems over time. So it's kind of a neat idea here. As we get started, kind of spent a little bit of, I think, 10-15 minutes on this earlier tonight before this started. And the idea is that we'll have a single Go routine, since this is in Go, that will manage the main app. It'll keep the main app up. And then what we'll do is we'll send on a channel anytime we traverse the grid, the location we're traversing at. Every time we make that decision, we'll send that down a channel, and that channel will then process that data and then periodically refresh the grid. Maybe we'll do it on each update. Not really sure yet exactly how we'll implement that, but the challenge is that, traversing speed versus, being able to actually show something visual to the user and not just have it done immediately, right? So I think that'll be the idea there. We can utilize channels for that. It's a great, big use case for channels. Personally, I haven't done a whole lot of desktop application development, especially even in Go. Well, I'll take that back. I did a lot of desktop application development in Delphi back in 2005, 2006. But these days I do a lot more back-end infrastructure. So just kind of some ideas there for where we might see this head with this framework. But as of right now, yeah, we'll dive into day 9 here shortly. I might also do this in such a way that it can be printed on the terminal, and we can do something where it's more terminal based as opposed to, in a desktop like app here with Fine. I do know that there are limitations in the terminal, and with the size of the data here, it's almost eligible or illegible, or you can barely read the data that's here. So there are some limitations, but for all intents and purposes, we should be able to traverse this grid and kind of get some updates. So that's kind of the pregame. I like starting things a little bit early here with the stream, just so this is what I call the pregame portion of the stream, kind of get my mind flowing, and we'll see how well we can tackle the problem tonight. We'll just see how it goes. Maybe, yeah. Did notice one thing here, if we're kind of curious about the leaderboards. I obviously have not ranked anywhere on the leaderboards, not that fast at all. But I was curious about my personal times, and so I can get my personal times by going here. Obviously, day 7 was a really bad night for us, but this gives us an idea of how long it took us to get through each problem in each day here. So that's just kind of the idea where we rank in comparison to others. I'm not doing this for rank. I'm doing this just to exercise my own ability, and I figured I could share the journey with everybody else here. So that's what I'm doing. Right. So we got 6 minutes and 4 seconds left. Just wait here for a second. If we dive into this implementation here where we visualize, so far what I've done is I've kind of built out this matrix library, and it really is for my own benefit, but we have the ability, there's a library called Find, which allows us to build these GUI objects, and based on the stringified grid, we can then use those properties. Actually, these no longer matter. Probably come back to that at a later time, but we can build this from that stringified grid. So as we build these like matrices or grids, we can visualize them as we go. And then, like I said, we can kind of do some updates with this to actually show path traversal. So I'm kind of interested to see how that goes, where we're not just solving the problems, but we're visualizing the problems in unique ways. So just some fun time for myself. All right, we got 4 minutes and 46 seconds. One of the things that I really am wanting to focus on here is as we continue to develop and move forward with this is maybe fleshing out some of the testing. I've tried to really take I don't want to say test-driven development approach, but kind of there's a test case in every single one of these. So the idea is that if we know what our inputs are and we know what our expected outputs are, we can do some test-driven development. Well, let me take a step back. We can write tests, or we can utilize tests. I don't typically take a TDD approach. I think the idea of completely building your test first, then developing against your test is difficult and somewhat impractical. But once something is developed, having tests for every bug, every issue, every edge case scenario that you find is absolutely imperative to application development. It ensures that tests ensure that you have good contracts between expectation and functional output. Iterating on those tests ensure you don't break old contracts, but can satisfy new contracts. So I look at it as a guarantee of this is our anticipated input, this is our expected output. and they ensure that we have good code quality moving forward. Ensure we don't break things. Ensure we do things can we do things at speed with some sort of guaranteed reliability. And so I think it's absolutely critical that we build tests into our applications. I've been in development environments that tested not at all, and if I can help it, I'll never be in that again. Testing is critical to your infrastructure, critical to your application stability, and it really does guarantee long-term success of your application. So got 2 minutes and 19 seconds. Let's just test the basics here. We'll run day 9. Should give me nothing. And then if I test, we test day 9, and we should get a failed test. Okay, so that's good. 1 minute, 54 seconds. Let's just go ahead and close all these, and we'll go with that and that. All right. See what we get today. Has anybody completed day 7 or I'm sorry, day 8 already? I've only peeked at it briefly, but I have not attempted it or walked through it. I was busy last night and did not have an opportunity to run through it when it first came out. So that's on my to-do list for later, but we're moving forward with day 9 today. Right. $50 seconds left. Should probably go ahead and create a day 9 board. Five, 4, 3, 2, 1. Day 9, disk fragmenter. Another push the button leaves you in the familiar hallway of some friendly amphipods. Good thing you each somehow got your own personal mini submarine. Historians jet away in search of the chief, mostly by driving directly into walls. I'm going to skip most of the story here because that's not super important. He shows you the disk map, your puzzle input. He's already generated for you this example. This disk map uses a dense format to represent the layout of files and free space on the disk. The digits alternate between indicating the length of a file and the length of free space. So a disk map like 1, 2, 3, 4, 5 would represent a 1 block file, 2 blocks of free space, a 3 block file, 4 blocks of free space, and then a 5 block file. A disk map like 90909 would represent 3 9 block files in a row with no free space between them. Each file on the disk also has an ID number based on the order of the files as they appear before they are rearranged, starting with ID 0. So the disk map 1, 2, 3, 4, 5 has 3 files, a 1 block file with ID 0, 3 block file with ID 1, and 5 block file with ID 2, using 1 character for each block, where the digits are the file ID and dot is free space. The disk map represents these individual blocks. The first example above represents these individual blocks. Okay. One, 2, 3, 4, 5 represents, because 0, and then 2 free spaces, and then 3 is 1, and then 4 free spaces, and then 2 with an ID of 5. The amphipod would like to move file blocks one at a time from the end of the disk to the leftmost free space block until there are no gaps remaining between file blocks. For the disk map 1, 2, 3, 4, 5, the process looks like 0, 2, 2, 1, 1, 1, 2, 2, 2. The first example requires a few more steps. The final step of this file compacting process is to update the file checksum to calculate the checksum, add up the results of multiplying each of these blocks positions with the file ID number it contains. The leftmost block is in position 0. If a block contains free space, skip it instead. Continuing the first example, the first few block position multiplied by its file ID number are 0 times 0 equals 0, 1 times 0 equals 0, 2 times 9 equal 18, 3 times 9 equal 27, 4 times 8 equal 32, and so on. In this example, the checksum is the sum of these 1928. Compact the amphipod's hard drive using the process he requested. What is the resulting file system checksum? Be careful copying and pasting the input for this puzzle if it's a single, very long line. All right, let's look at the puzzle input. Okay, well, that's a lot. So let's see here. So we have 2 blocks of 0, 3 blocks empty, and 3 blocks full, and 3 blocks empty. And so I think, just kind of thinking through this process, we should be cataloging the positions of the frees as like an empty index, and we should somehow, instead of this being a 2, we should replace it with a 0 index, comma 2 as the first position in the slice, this as empty 3, this as 1, and we can process that first. Then once that's done, as we can see here, we want to move bits from here to here. We can actually do this in chunks. So meaning that if we have 9s and we've got free space, we know we can move all of the 9s to fill it. Then we can move all of the 8s to fill what space is there. Then we can move to the next slice and we can move the 8s. And if the ID is different, then we can insert into the slice after the initialization whenever we have to insert a point. So like in this case where it's 998, and then instead of, it would be, really it's just index and block count, index and block count, right? The fact that the second number is always free space doesn't really matter. And then once we do that, that will be a lot less moves because we can do that like math. And it's from there, it's like, okay, well, we can step through this and say, okay, 0 times 0, 0, whatever, and then this is the index position. So the index position will always be the previous, it will have to be a running total, but we can calculate that because it's always going to be the length. It'll be the ID and length, ID and length, ID and length. And we do know one thing. Do we know that one thing? Okay, so these aren't the indexes. Okay, so the indexes are based on these. So yeah. Okay. It's a very long string. Got it. All right. So we'll go with this and we'll copy this into our test. This is our test input and our result expectation is 1928. And then, so this is zeros, but this isn't the index. The index is 0 because it's in the 0th place, not because it happens to be at the beginning. So just like this is a 2. I also know, well, let's not get too distracted right away. 1, 2, 3, 4, 5. We could also probably calculate that, but so let's see how we want to do this. We can do a split here. Let's go here. We've got our input, so we're going to do bytes.split s, and our separator is going to be that. So yeah. Yeah. Okay. So that's going to be our numbers or our values. And then if we do we'll just do a strings.split and we'll convert this to a and we're going to do a block. We'll call it a type block struct. And it's going to have an ID, which is going to be an int. And we're going to do size, which is going to be an int. And if the ID is -1, does that matter? Well, does the ID actually matter? Where does the ID matter? Continuing the first example, the first few blocks position multiplied by its first ID number. Its files number are 2 times 9, 3. Okay, so it does matter. 4 times 8 equals 32. 0, 1, 2, 3, 4. So I feel like this is deceptive. The final step of this file compacting process is to do this. Continuing the first example, the first few blocks position multiplied by its file ID number are 000. So the file ID number, each file on disk also has an ID number based on the order of the files as they appear before they are rearranged. Right. Okay. So it's deceptive in the test because it says that this is 9 and 9 and then 8, but I think that's actually the issue. We have to make sure we bring the file ID with it, which is fine. It initially is set to 9 and 8 respectfully, I think, but then the file ID is based on what? Before they rearrange, starting ID 0. Whereas 3 files, a 1 block file with an ID of 0, a 3 block file with an ID of 1. Okay, so that is the number that's being brought over, but not necessarily the size of the block. So when we split the block, we'll need to know how many are filling in. So, okay. So ID, yep, that's fine. So then what we can do is just create a slice of blocks, and then what I'm going to do is for each block, let me, we'll do that, and then we'll say if I think that's right. We'll do that. So on the first one, I is 0. So I think 0 is actually the block of the number is the file. Each file on disk also has an ID number based on the order of the files as they appear before they are rearranged. Starting with ID 0, so the disk map 1, 2, 3, 4 has 3 files and one block file with ID 0, 3 block file, etc. Yeah. Okay. So that means that let me get my head wrapped around this for a second. So the ID is going to be 0, is going to be I for the first one. Okay. And then yeah, why is that a problem? Okay. And the size is going to be size. So we'll call this ID equals 0. And then this will just be ID ID plus plus. We'll increment it each time. And that'll be on the first one and then every other one after that. Otherwise, we are going to create a block. And so we'll do blocks equal to append block blocks B, right? This should be a slice. And then I'll do the same thing here. And this will be -1. Right, so we're going to create these initial sets of blocks and we're going to base them on the ID based on where it's positioned in the file. And then we have the particular size. So that's kind of part one. We just go ahead and initialize that set. And so now we have to move everything from the right side to the left, filling in those blocks. So I don't really care about, I don't so much care about the what do we call it? Yeah, all the way until they're like this. So this is our initialization. So then what do I want to do? I want some sort of for loop. And so what I have a couple of conditions here. Anytime there is still empty blocks, we don't have a continuous string of blocks. But I can always loop by popping off the very right of the list. grabbing the very right and checking to see if there's any room on the left. And if there's not, I insert it back onto the right. Yeah, because this isn't ordering it right. So I just always grab the thing on the right and try to insert it starting on the left. So I guess I can create a free blocks index, which I know is going to start at 1. We'll call it next free. And that's going to be the position we're going to start looking at. And we are going to in this particular case, there are no free blocks on the right. That's interesting. I wonder if that's true for this or not. How do I check that? If I copy this input, I'm looking for input that is $2,000 20,000 characters total, so that's an even number. And our test input is also even. So that means that the last one is not an empty block. It's going to have something in it. So we kind of rely on that, and we're going to iterate. And so what we're going to do is we're going to say is blocks is the length of blocks minus 1. And minus 1. And so that's the block we're looking to move. And then we're going to set blocks equal to blocks. We're just going to go ahead right now and we'll see how this works out. So they were optimizing in other ways. We're just going to go ahead and set it to we're going to set it to 1 less, right? So blocks is now adjusted. Okay, that's interesting. It is possible for us to have free space on the end. So I can't just take the last one. I have to loop through the blocks. Let's worry about that in a second. Let's finish this part out, but I'm gonna have to determine what blocks or what block I'm going to essentially pluck out, which index, right? So, right. So now that we have a block, right, we're going to start at our next free. and we iterate forward, and we just keep moving forward. Next free, we're just going to use so that we can jump forward to our next free block as we go, but we know that we're starting on 1. So we're going to do this. We're going to say if move.size is less than or equal to actually, can I do this a different way? Free is equal to blocks sub I. And we can say that free yeah, we'll do it this way. If free.size is less than our move.size, then we're going to say free.id equal to, let me do it the other way, free.id equal to move.id. No, changing that around. And then we'll break out if we're 0. Then we'll say blocks sub I equal to free, and we'll continue here. Okay, so that's the case where that all of what is free can consume what we have. Otherwise, we know that what we have move is larger than free. Let's say less than or equal to, because if we're equal to move.size, we can move everything in there. So what's the other condition? Well, the other condition is we have more to move than we have free space. So if free.size less than or equal to move.size, or less than, I'm sorry. Less than. Or equal. Or equal. My brain's not working today. Sorry. Free.size is less than move.size. We know that we have all this, we don't have enough space here. And we're going to do move.size plus equal free.size. Right. So minus equal. So we just deposited a portion of what's in move, assigned it to the free, and went forward and just reduced the amount we had to move for that given index. And we're going to say what we know is if we'll call this next actually instead of free. And we'll say if next dot ID equal -1, we continue, or not equal -1. Because we only want the things if they have an ID assigned, then that means it's not free. So, or that means that there's something occupying that space. Okay, and then the last condition is if next.size is less, we're going to do, and then we're going to iterate to the next one. The other condition is if it's more, right? So if it's more, move.size equals 0, break. If next.e not equal -1, continue, we go to the next one. If next.size is less than move.size, we add to it. Otherwise, the last bit here is we take over the current and we create a new one. So if next.size is less than move.size, so if it's greater, then what we have to do is we still do this, right? Maybe we can simplify this. Move.size equals 0. But there is a new free is going to get an ID. This is going to be a block. And it's going to be -1 for the ID. And then for the size, it's going to be well, this is already defined up here, so why am I? Box ID equals next. Hold on a second, let me. Oh, that does have to happen, but that can happen down here. The size is going to be, since we know we have so our new free is going to be that. And we're going to do a blocks.insert, slices.insert, insert. And we're going to be inserting into blocks at index new free blocks at index I. Let's see here, insert. Did I get this data backwards? Yeah, so insert into blocks. Okay. I think this can be simplified a little bit, and we might do that here in a second. Yeah. All right, let's okay. It's working. Mm, let's check the blocks slice out. Make sure I didn't mess that up. Zero, -1. Those all look good. Okay. So why? Okay. I think it's because I'm just like recursively deleting out of it and eventually it just gets down to 0. Yeah. Okay. So that's what's going on here. So well, first off, size of -6 shouldn't be true. Um, well, okay, that's next dot size less than move dot size. Where do I get into this negative? Next dot size is less than move dot size. Oh, minus move dot ID. Okay. Okay. All right. So that's better. Okay, so then the last thing is what I think I'm doing is I am constantly grabbing off the right side, but if at some point I'm not reappending back. So what I mean by that is I'm popping something off the right every time, the right side of the stack, and I'm trying to find its place in the left side of the stack. And if I don't, then I'm not putting it back on the right, and then I'm just kind of recursively going until there is no more. So what I need to do is I need to check to see at the end of this if greater than 0 and if that's true, then we break. But before I break, I need to set blocks equal to append blocks sub move. So the thing that I'm moving, I'm just going to put back on the end, and then that should be it. So then that should give me something. If we look at our test input, if we go back here, I should get, we can look at this and say, okay, I've got 0 for 2. I've got a block ID of 8 for 1. Block ID 9 for 3. 1 for 3. Okay, why did this... Oh, because the insertion... Okay. So if I go back to the insertion, is it I plus 1? Is that what it has to be? Before we actually do our calculation here, let's just kind of map this up here. So 0 for 2, 9 for 3, 8 for 1, 1 for 3, 8 for 3, 8 for 3. Okay. 7 for 0. Okay. That's a little weird. 2 for 1, 7 for 3, 6 for 0, 3 for 3. Why are we getting this 7 for 0? It's a little odd. Hmm. Is this the problem here? If we're creating a new free, next, What about the equal case? Is that the problem that I'm creating a new free of 0 when I don't need to? Is that what is going on here? Let me just see if that's it. Okay, let's see here. Let's compare these results. 0 for 2, 9 for 3, 8 for 1, 1 for 3, 8 for 3, 2 for 1, 7 for 3, 3 for 3, yeah, 6 for 1, 4 for 2, 6 for 1, 5 for 4, and then 6 for 2. Okay. So that is right. I think I can clean this up a little bit, but I'm going to just move on for right now and actually do our calculation. So then to calculate, we do it based on the file ID times the index position. So it's index position first times file ID. So yeah. So then to score it, we'll call it score 0, and we'll say for blah. Plus equal our block dot ID times our block dot size. And then we return our score. Okay. The first few blocks positions multiplied by its file ID number are, okay, so it's the index, sorry. It's the index. But it's the I first times block ID. Okay. Okay. So then we actually have to do for, we have to range through our block dot size. That's what we got to do here. Oof. So we have to iterate forward each time. So if we have like the block ID that we're in has to move forward with the block dot size, because it, you know, even though we're n number of things forward, so really it should be called position. And so I actually think we can get rid of that and call position plus plus, and then this is position times block. Maybe. Okay. Do we have any empty blocks at the end? I know what I wanted to do. I just didn't do the right thing. And we'll call this block.id. Maths. So we've got 0, 0, 1, 0, 2 times 9. I mean, that all looks right. 2083. And my sum is 1928. 2083. Well, okay. The first example, the first few blocks position multiplied by its file ID number are 4 times 8 equals 32, okay. 9 times 27. Wait, I don't understand that part. I don't understand this. Zero, zero, 1 times 0, 2 times 9, 3 times 9, 4 times 8 equals 32. Two times 9, 3 times 9. Oh. Oh, I've got a issue here. I've got an issue here. Okay. So if the next dot size is less than the move dot size, that's fine. The new free is that. Okay. But the is that the difference? Yeah, okay. So probably shouldn't be printing out all these lines. Let's just get rid of those real quick. Yeah, definitely not those. try it out, see what we get. Awesome, part 1 is done. Continue to part 2. Upon completion, 2 things immediately become clear. First, the disk definitely has a lot more contiguous free space, just like the amphipod hoped. Second, the computer is running much more slowly. Maybe introducing all of that file system fragmentation was a bad idea. The eager amphipod already has a new plan. Rather than move individual blocks, he'd like to try compacting the files on its disk by moving whole files instead. This time, attempt to move whole files to the leftmost span of free blocks that could fit the file. Attempt to move each file exactly once in order of decreasing file ID number, starting with a file with the highest file ID number. There is no space on the free to the left of a file that is large enough to fit the file does not move. The first example from above now proceeds differently. Okay, so very similar, but we only move if we have enough space. So if we don't have enough space, we don't move it. The challenge is, oh, that's interesting. Is this condition of 8 here surprises me. That once 8 was checked and it moved before 8, it never came back. So I was expecting maybe 8 to slide over to here, but that's not the case. So we just need to move from the right. We grab the rightmost index, check all the left all the way up to said index, and move only if it's a whole block. So we can take 2858 for our test input. We'll undo this. We will just use B1 because it's the same input. We don't have to use a separate input here. We didn't modify it at all. Or just B. And then for part 2, man, I'll clean this up in a little bit, but what I'm going to go ahead and do is just copy this in its entirety and then just modify it because actually I think in some ways, well, let's not get ahead of ourselves. So well, that's kind of interesting. So the file checksum is the same. Now as example, checksum would be instead of using the resulting file system checksum. So the only thing is these are empty space. What do we do? It's the same, but the same didn't really include free space. I guess the way that I did it didn't really include free space. Yeah, I think I can just simplify this a little bit by walking the index backwards. So trying to think about how we basically don't want to do this, right? We're not gonna be splitting the index. We're gonna continue to walk, right, until we find a condition where the move can take place. Otherwise, only if it's the next dot size is less than or equal to our move dot size. If it's anything else, we don't want to do this. And let's see here. So as far as our indexes go, instead of popping the last one off, I mean, we can pop it and then reappend it, and that should be fine. But it's not always going to be the last index. So we can wrap this and say for j is equal to length of blocks minus 1. J is greater than or equal to 0. J minus minus. And that'll be our, basically how we're going to walk from beginning to end. And then we'll go here. And then our this becomes J. We're going to move J. And I is less than whatever J currently is. And if we are successful, blocks slices dot delete blocks 1 1, or I'm sorry, J. Is it J? And then is the J a length? So only if we're successful do we delete that block. So I think unreachable code. Why is that unreachable? We don't want to do this anymore. Oh, it's interesting. I actually didn't take advantage of next free at all. In that previous, I could make it better with the next free, but oh no, I did actually. Next free has to go away. Next free has to be 0 here. Yeah, we'll just do that to simplify. I didn't set next free ever previously, so that's fine. Maybe. So J is the length of blocks minus 1. J is greater than or equal to 0. J minus minus. Greater than 0. And 1. Delete removes the element si colon j from s, returning the modified slice. Delete zeros the element s length. Is it j plus 1? I always get this mixed up. So why can I not delete j? Oh, so next has to be greater than or equal to move size, not less than or equal to. And next dot ID. Oh, I see what I did wrong. I copied the wrong block. I don't want it needs to be this, but what we want is if the next dot size is less than move that size, we just want to move to the next thing. That's what we want to do. But then if we insert it, which is what we're doing here, we also want to delete j. So not that. We want to which is what I was doing earlier. Blocks j1, I think, is what we want to do. So blocks equal. I don't know if this break is necessary, to be completely honest. Okay, let's think about this for a second. So if it's not equal -1, we continue. If the next dot size is less than move dot size, we continue. Otherwise, next dot ID equals move dot ID. We create a new free block. We set the next size to move size. I guess I could optimize that by changing the size and just doing an insert, but blocks I equal next. If a new resize is greater than 0, we insert it. The move size equals 0. I'm not convinced this is needed. This move size is always going to be 0. And then is this again j plus 1? Is that I always get that. Okay. We're right here. Right here. It's the only one. Delete. There we go. Okay. Yeah. And then so what's our final block here? Let's just look at that. And let's compare it to this. So we've got 0, 2, 9, 2, 2, 1, 1, 3, 1, 3, 9, 2. Oh, wait a second. It's not deleting. Looks like it's inserting or it's moving, but the original block. That's I to J from S, returning the modified slice. One comma two. I see this is like confusing to me. Yeah, it's so J, if that's the index I want to delete. It's the elements from and including index I up to excluding index J, or if you remember the math notation for interval IJ. So I think that is it, right? Am I just like, can I just not do this here? I mean, seriously. I don't understand why this is so difficult. It it's supposed to be the index that you want to start at. So index 1, so not 0 but 1, and then 2 2. So that'd be index J plus 1 should delete J. J of J does not delete anything. That's why it's not actually changing. J of J does not work. So if I delete J, is it because I need to break out of this once I do that? Is that what's going on here? Okay, that's better. And then we still have an issue. Okay. Why? 0 of 2, 9 of 2, 2 of 1, 1 of 3, 7 of 3, 4 of 2, 3 of 3. Okay. Why didn't you delete? That's my next question. Mm-mm. So they moved, but the original was not deleted? 18, 20, 16, 19, 18, 15, 17, 5, 13, 5, 12. Yeah, they deleted down. Um, um, so why do we still have 9 of 2 here? That's absolutely bonkers. Okay. So 0, 2, 9 of 2, 2 of 1, 1 of 3, 7 of 3. Nope. Yeah. Six of 4. I just want to delete the last one. I don't want to delete the last one though. It's not true because the last one may not be the block that needs to be deleted, right? We're starting at the length of blocks -1 and we're decrementing until we're at 0. So, and then we're incrementing up from there. So it's not necessarily I'm just going to do it the non-other way. Like, is that a better result? I don't understand why I'm still getting this. That should error out in the first iteration because they're 9, right? Yeah, what in the world? Why is the ninth block not deleting? J is the length of blocks -1. We're not appending in part 2 to the block slice at all. You know what? I actually am going to change what I'm doing here. Let me just set blocks of j dot id equal to -1 and block id dot size equal to 0. Let me try that. And then what I can do. Um, I don't understand this. Why is this still here? For I is 0, I is less than j. J is established here, j is decrementing, I is incrementing. I should never get to a point where it passes j. Oh, I'm an idiot. For this one, these should be j. Continue that. I'm so perplexed. All right, I need to just step through this. Why is it that if j is being set to the length of blocks -1, j is greater than 0, j minus minus 9, day 9 block, size 2, is getting moved. But then, for some reason, delete 18 of 20, delete 18 of 20. So it's like it's skipping, but it's not. It's just not getting to the delete. So why is it? Hold on. What's the input here? It's 9 of 2, right? Yeah. So we're moving 9 of 2. Okay. Mm, 4 ID 4 size 2. Yep. Okay. 5 4. Oh, that's not right. 3 of 3. Mm. Ah, I think I see the problem. Maybe. Maybe. We're inserting the new free block before we're setting the other one. Yes. Okay. So that's better, I think. Let's compare the results. So we've got 0 of 2, 9 of 2, 2 of 1, 1 of 3, 7 of 3, 4 of 2. I realize I got these empty spaces here. That's okay. 3 of 3. 5 of 4. 6 of 4. 8 of 4. Okay. So what is not right here? Why is our score now not correct? So is our index on the empty spaces important now? Because in the previous example, we filled up all those spaces. So those indexes are different. Do we have an issue now with the indexes having to be the accumulated empty space that was still there? So for instance, we've got 7 of 3 and -1, 0, and then 4 of 2. Should that actually be a... Do we have to consider that still? Is that the difference? What's our number? Our number is too low, and I think that would probably make the difference. So why are our blocks this? Why are they -1 and 0? -1 and 0. Is that happening because if the next ID is that, that's fine. -1 and 0. Okay. Oh, I see. I think I understand. My problem is just because new free let me do this then. Let's do block. We're going to try this again. We're going to do blocks equals slices dot delete slices j block, sorry. Right. So okay. So this looks a little bit better. So then I think what we have to do is if we come back here in our score calculation, it just simply is right. Maybe. I don't understand this part right here. So the 2858, let's look at my block output real quick. So we've got 0 for 2, 9 for 2, 2 for 1, 1 for 3, 7 for 3. Oh, there is an empty space here. Why are we missing? Aha. So I don't want to delete, actually. I don't want to delete. That is a mistake. That's a mistake. I actually want to set okay, there we go. Yeah, I thought about changing the format of the output as well. Oh, that's not the right answer. All right. So 1329, 1329, 98833, 98833. Okay. Yeah, so this is definitely a part of it here. Um, so if we move 3, it's always going to be 3. I don't have to change this back. I only have to change where it's going. Next to ID, next dot size needs to be the move to ID, move dot size. I mean, we could do that real quick if we want. If we want to just real quick, if we um so if we've got this here, we can just log it with it, and we can do a um say if block.id equal -1. And we can do strings dot repeat, right? And we could do size. Otherwise, it will be let's just suppose we'll do not super efficient, but it'll get the job done. That's what you're suggesting here. I mean, that all looks fine to me. I'll get rid of this. So change this to just be embedded in here. Get rid of that. Why would the test be passing and the actual output not? What did I miss? Like what property? Oh, you know what I missed? I'm an idiot. Yeah. I provided the output of part 1 to part 2. Yeah. At least I thought that's what I missed. Yeah. I thought it was that, but apparently not. So, I mean, there's large parts of this file that should be maybe corrected and it's not. We'll ignore part 1 for a second, because that's fine. j is greater than 0. Yeah, I mean, we can include 0 on that. I is less than j. Well, when we check these blocks, we don't ever want to include something that is itself. So I think that's fine. And I mean, we can remove this. And okay. Oh, well. So the new free block is the next dot size minus the move dot size. If we move something from j, we always want to free it. The new free block is always to the right of I, which is where we are. So for shifting something to I, we insert to the right of it. We know that's right in the tests. So if we break out of here, we go to the next iteration of j. Better just to get rid of this variable entirely. There's no confusion. If next Get rid of that. Just reduce these variables for a second. Same output. Yeah. Let me get rid of part 2. Actually, I'll leave it in. I'll get rid of it. Just so it executes a little faster. This breaks us out of the I loop. So once we find a large enough space, so if the block size is less than the block size of J, so if we don't have enough space, we continue. If they're equal, we want to take up the space. And then it is going to be, the new free block is going to be what it currently is to what we're analyzing against, which could be 0. I don't really care too much about that here. The current block, the earliest block closest to 0, is going to get the ID of J. It's going to take on the size of J. And then, oh, wait a second. Yes, it's going to take on the size of J, because if we're moving 3 nines, all 3 nines are going to go here. In this block, which would have been larger, has now become smaller by the same 3. And then the previous location just becomes a -1 for the ID, because those blocks are now free. And then we are inserting potentially into, this is the issue. This is, I think, where the bug is. Because I'm expanding the slice, the size of the slice. I'm manipulating the size of the slice. Yeah. So since I'm iterating through the slice, not necessarily indefinitely, but I could expand that set of the slice so that J is either at a point before where it gets expanded, or something will get missed in the recalc because of it. So that means I need to do what? Would it be better to maintain a second slice? No, certainly not. Certainly not. Yeah, so I think it probably would be dependent on the exact output. Um, or the depending on the input, because everybody's input is different, or at least some variation of different. I don't know how different. I don't know if advent of code has like 10 inputs that it provides to varying people, or if there's one input. I'm not sure. But I think that's where my bug is somewhere in that edge case. And I'm trying to think of how I want to handle that. And the reason why I say that is because in this example here, uh, here, 888 is never reprocessed. So, okay, it might be. I don't know how variant it is. I know that the creator just dropped like keynote like 9 days ago that talks about advent of code. I want to go back and look at it. Um, but yeah, so we don't want to reprocess an index, but the white space, at least, let me go back to my calculation here. If the block ID is -1, we still care about those positions, those indexes. So it's not like I don't care about them. Otherwise, I would just get rid of them, but I actually do care about the relative empty space that's in between for the overall calculation. We just we just increase our block size by that, right? So that tells me that I do care. So I want to keep them. Yeah. Yeah. Okay. I think I understand what I need to do. So instead of depending on for j and length of blocks, what I can do actually is get the ID, which will just be the blocks length of blocks minus 1 dot ID. We'll call it per ID. And then instead of for j, I'll just do this. This is going to take a little bit more processing, but it's a lot of extra looping, but the way that I've kind of committed here, I don't really care at this point. So Otherwise, if block.id less than equal to cur id minus 1 equal to block. Um, yeah. And then try that. See if this is it. It's definitely a different value. Awesome. Right. So a little ugly, but what I chose to do, just because I was already committed to this, I think maybe I could have used like a linked list instead. That might have been a little bit better instead of dealing with these slices and indexes. But what I decided to do was I would just create this cur ID. So that was the file index. That file index gets set initially. And then I plussed it by 1, which is really ugly. But I did that so that when we enter this block for the first time, it'll look for the next cur ID or the cur ID that is decremented by 1. And then we essentially, what we're doing now is we're going by that index, that file index, and we're saying, give me the previous to that. It probably would be more efficient to go backwards to get that ID. But then once I find that ID, I simply say, okay, let's break since we know what J should be. And then I go through that same process, iterating from the left side forward to what J is. That way, no matter what I've processed, what I've moved, and how I've resized blocks, we're never going to be in a position where we're dependent on that initially. And we could always kind of go from that backwards, and it wasn't that slow. I think probably what I'd want to do is for I equal the length of blocks minus 1. I is greater than or equal to 0. I minus minus. And we would do and then this would be block, just to keep things easy, sub I. And then we would go through that same process, and 64, yeah, we'd probably get the same value. Yeah, that should be a little bit faster. I don't know how much more faster we want it, but that should be it there. So let me get rid of this debug output. What's the other? think a lot of the speed here is just printing at the screen, honestly. Yeah, so it takes less than a second. Okay. Well, that took a little bit. Yeah, not too bad. Let's see if we can clean some of this up. I'm just going to do a little bit of refactoring. See if I can make this any better. All right. Well, I think that's it for tonight. Maybe I'll pick up part 8 that I skipped tomorrow, but I'm glad I got through it. Took a little bit extra time, but here we are. Thanks for hanging out. Appreciate all the love and support, and if you could, like and subscribe, and we'll do more of this. Maybe in the future actually build something instead of doing some coding challenges, but at any rate, I will see you all next time. Y'all have a good night.